Hello, welcome back, everyone. Welcome to my presentation on statistical mechanics of glass. My name is John Morrow, and I'm a professor of materials science and engineering at Penn State University College of Earth and Mineral Sciences. Today, I would like to give you an overview of the statistical mechanics of glass. Now, statistical mechanics is a field that was first invented by Ludwig Boltzmann back in the late 19th century. This was a really controversial topic at the time that it was invented. Boltzmann was basing the field of statistical mechanics on the concept that all matter is made up of atoms, and this was a very controversial topic at the time. Many prominent scientists of that day did not believe in the existence of atoms. And what Boltzmann postulated was not only that matter, all materials were made up of atoms, but those atoms could adopt different configurations. Those configurations appear with different probabilities. And if you do a weighted average of all the different configurations of atoms in a system based on their relative probabilities, that would give you the average behavior of the system. So the field of statistical mechanics is based on this notion that all of the macroscopic properties of the material, although the properties that we measure are a result of the atomic configurations of the structure. And that if you do these weighted averages, then you can calculate what the macroscopic properties of the system are. So this was controversial for multiple reasons. First was that he was building upon the notion of atoms. Second is that Boltzmann was adopting the field of probability and statistics from mathematics, which in the 19th century was also a very controversial subfield of mathematics. Many scientists assumed that it was only useful for gambling, and thus it was deemed to be kind of an immoral branch of mathematics. So Boltzmann was taking this immoral branch of mathematics, combining it with this very controversial notion of atoms, and then developing this entirely new field of statistical mechanics. He faced quite a bit of bullying at the time by other scientists, such as Ernst Mach, who just flat out rejected Boltzmann's entire life's work. Unfortunately, this ended really tragically for Boltzmann. He took his own life. He was buried and his work was forgotten about for about 20 years. Later on, some of the younger scientists of the day, like Max Planck, rediscovered Boltzmann's work and found, that there was a lot of value in the work and kind of resuscitated it. And the good people of Vienna actually dug up Boltzmann from his very humble grave, and they gave him this much more prominent burial that you could see today if you go to this cemetery in Vienna. He's buried next to some of his musical heroes like Mozart. It was really special for me one time when I received this photograph here that was taken by one of my former students who brought my kinetics book. I don't know if you have a copy of this book, but Materials Kinetics here. He brought a copy of this book to Boltzmann's grave and laid it there at his tombstone. But if you look at the top of Boltzmann's grave here, you'll see this equation that S equals K log W. In more modern textbooks, you'll see it expressed as shown on the right-hand side here. S, which is entropy, is equal to K, which is Boltzmann's constant, times the natural log of, and then usually nowadays it's expressed as omega, where omega is the number of microstates, or the number of different atomic configurations that yield a particular macrostate. This is Boltzmann's equation for entropy, and it was really a groundbreaking equation because what it did was connect the microscopic physics of the system based on the number of microstates to a macroscopic property of the system, the entropy. And Boltzmann knew that there would be some proportionality constant between the two, which he labeled as K. He never actually determined the value of his own constant. The value of Boltzmann's constant was determined later on by Planck, who determined Boltzmann's constant to be simply the gas constant here, R, divided by Avogadro's number. So this is equal to 1.38 times 10 to the minus 23 joules per Kelvin. Of course, Planck has his own constant, and therefore K is known as Boltzmann's constant. But the great thing about this is that this is connecting, um, the microscopic physics of a system based on the number of different atomic structures that a system can adopt with a macroscopic thermodynamic property, in this case, the entropy of the system. What we would like to do in this presentation is to see how statistical mechanics can be applied to glassy systems. And what makes glass so interesting is that it is a non-equilibrium material. If we want to understand where glass comes from, we can use this volume temperature diagram shown on the right. And a glass is continuously connected to the liquid state. So if we start up here in the upper right corner at high temperatures and high volumes, this is a liquid. And if you cool the liquid below its freezing point, if the liquid were to stay in equilibrium, it would crystallize. And so it would undergo a first order thermodynamic phase transition, going from this liquid line down to the crystal line. Um, and then any continued cooling of the crystal would mean that it would follow this crystal line here at the bottom. Now, crystallization takes time. It takes time for the atoms that are in the disordered liquid configuration to rearrange themselves into a perfect crystal structure. And if you were to take this liquid and cool it so quickly through this gray region where crystallization is likely, you can get what's called a supercooled liquid. A supercooled liquid is just any liquid that is cooled below its normal freezing point. From a thermodynamic point of view, this is known as a metastable phase, meaning that if you just leave the supercooled liquid unperturbed, it would be stable on its own. But there is a possibility of lowering the free energy of the system, finding a more stable phase by undergoing a phase transition. So the supercooled liquid, while kind of metastable if it's left unperturbed, can find a more stable equilibrium if it undergoes a phase transition to crystallize. Now, the supercooled liquid, if you were to continue to cool that, the viscosity of the supercooled liquid continues to go up, and eventually the time scale of the flow of the supercooled liquid becomes very slow compared to your observation time scale. And when that happens, the supercooled liquid undergoes this glass transformation or glass transition. This is not a thermodynamic phase transition. This is a kinetic transition due to the kinetics of the supercooled liquid becoming slower and slower. And when they become slow compared to the time scale that you're observing them on, what we observe is a gradual freezing in of that supercooled liquid into a material that feels and acts like a solid. And this is what we all know and love as a glass. And the glassy state is shown here on the left. Glass has properties that some of these properties are like a solid, like the mechanical response of a glass, but the structure of the glass is a liquid-like structure because it comes from freezing in the structure of a supercooled liquid. So glass has some properties that are like a liquid, it has some properties that are like a solid, but it has its own unique properties as well because it has fallen out of equilibrium with respect to the supercooled liquid, which in turn is only metastable compared to the true equilibrium, which is the crystal. Now, because glass is a non-equilibrium material, this means that the properties of the glass depend not just on its chemistry, and its current temperature and pressure, but the entire thermal history and, if applicable, the entire pressure history of the glass. For example, the two lines shown here show that a fast-cooled glass has a higher molar volume compared to a slow-cooled glass. That's because with a more slowly cooled glass, we've given it more time to stay in its metastable equilibrium, and then it falls out of equilibrium from the supercooled liquid at a lower temperature. What this means is that we need some additional parameter to describe the non-equilibrium state of the glass. And the simplest parameter that we use to describe that is called the fictive temperature, or TF. Fictive literally means fictional. It is a made-up temperature, and it is some additional parameter that we use to give some indication of what the thermal history of the glass is, and therefore to give some indication of that non-equilibrium structure of the glass. Now, the simplest way to get the fictive temperature is to draw a line that is tangent to the glassy line and then see where that line intersects the supercooled liquid line. For the fast-cooled glass, that intersection point is here. And if you drop that down to the x-axis, this is labeled as TF2. This is the fictive temperature of the fast-cooled glass. We can think about that fictive temperature as being approximately where the supercooled liquid structure is frozen into the glassy state. So if it's a fast-cooled system, that happens at a higher fictive temperature. If it's a slow-cooled system, we can do the same thing here. Take a line tangent to the glassy line, see where that intersects the supercooled liquid, and then drop it down to the temperature axis. And that fictive temperature is labeled as TF1. So you can see that the fictive temperature of the slowly cooled glass is lower than the fictive temperature of the fast-cooled glass. And that's because the slower cooling rate gives the system more time to stay in its metastable supercooled liquid state and then only fall out of equilibrium at a lower fictive temperature. Fictive temperature is not a perfect means of describing the non-equilibrium state of the glass. It is merely a simple way to take one additional parameter and give some indication about where it's fallen out of equilibrium. And so, from a statistical mechanics point of view, glass is very interesting because it's non-equilibrium, meaning that we cannot apply the usual equilibrium physics to describe the system. Also, because of the disordered structure of the glass, we know that it doesn't have a perfect crystal structure, and that non-crystalline structure makes it especially challenging to model the glassy state. And then the other thing that makes glass challenging and interesting from the point of view of statistical mechanics is that the time scales on which kinetics occur in the glass are very long compared to our usual observation time scale. So what I'd like to do in this presentation is systematically go through how we deal with these long time scales and the non-equilibrium nature of the glass and the non-crystalline structure from the point of view of statistical mechanics and give you some of the key physics that we use to describe these interesting properties of a glass. So let's start off with the nature of equilibrium. There are many different definitions of equilibrium that you might find in thermodynamic textbooks. One of my favorite definitions of equilibrium was provided by Richard Feynman in his book Statistical Mechanics, where he says that equilibrium is, quote, when all the fast things have happened, but the slow things have not. And this raises an interesting question because it's relative, right? It depends on what is fast and what is slow. And this definition of fast and slow depends on your perspective as an observer. For example, let's consider this example shown at the bottom of the slide, where you've got a cup of coffee and there's some cream that was poured into the coffee, and this cup of coffee and cream is sitting in a room at room temperature. And you can think about different stages of equilibrium where on a short time scale, say on the order of a few seconds, there is some chemical equilibrium here between the coffee and the cream, where you get a homogeneous mixture of the coffee and cream, and it reaches that chemical equilibrium. If you wait for a longer period of time, say if you wait a few hours, maybe just an hour is enough, there will be a temperature equilibrium that is reached between the coffee cream mixture and the room, where the initially hot coffee cream mixture is thermally equilibrated with the room that it's in, and it becomes a room temperature. But then there's another equilibrium if you wait on an even longer time scale, maybe a week or so, where there will be a vapor equilibrium between the coffee cream mixture and the room, where a lot of the water would evaporate, leaving behind this little ring of what used to be coffee at the bottom of the cup. So the question becomes, which one of these is the true equilibrium? The answer is that it depends on what you're trying to do with your experiment. If you are trying to look at chemical equilibrium, then the relevant equilibrium is this one on a short time scale. If you are studying Fourier's law and you're looking at the exchange of heat, then the relevant equilibrium is this middle one. And if you are looking to study vapor equilibrium, then the relevant equilibrium is this one on a much longer time scale. And it's up to you as the observer, or from your perspective of the experiment that you want to conduct, to select the relevant time scale for your experiment. Now, this introduces the concept of ergodicity, which was a concept that was first proposed by Boltzmann in his development of statistical mechanics. What is ergodicity? So, in probability theory, an ergodic dynamical system is one that has the same behavior averaged over time as averaged over the ensemble of all the system states in its phase space. So, in other words, ergodicity implies that the time average of some property, we're representing time average here as being the property P with an overbar indicating the time average, and that time average is equal to the ensemble average of the properties. And if this is satisfied, then the system is said to be ergodic. So if a time average of properties is equal to the ensemble average, then the system is ergodic. If this is not satisfied, then the system is non-ergodic. Now, what does this mean? So we wanted to take a time average, what you would do is prepare like a single system and then measure its property values over time. So let's say you measure the density now, you measure the density 10 minutes from now, 20 minutes from now, 30 minutes from now, and keep track of all the density values that you've measured and take the average over time, and that gives you the time average. The other way to calculate the average value of, say, the density would be to prepare maybe 10 or 20 nominally identical samples. So you prepare, say, 20 different samples all the same way and measure the density of each of those 20 samples and then take the average. That would be an ensemble average. And if this time average is equal to the ensemble average, then the system is ergodic, at least with respect to that property. If these two values are different, for example, maybe you have a system that is evolving over time, and that if you measure the density over time, there's going to be some systematic evolution of the density over time, such that the time average is different from an ensemble average. If that's the case, then ergodicity is not satisfied, and so the system would be ergodic. Now, ergodicity is very interesting because this is an assumption that is used in a lot of statistical mechanics, and in many cases, authors don't explicitly state that they are assuming ergodicity. My advice is anytime you're reading a paper or a textbook and the authors switch between a time average and an ensemble average, they are implicitly assuming ergodicity, whether they state it explicitly or not. If they're switching between the time average and an ensemble average, assuming that they're the same thing, then that is making the assumption of ergodicity. And you want to kind of ask yourself, is that truly a valid assumption for that system or not? Another thing that we should note is the ergodic hypothesis. The ergodic hypothesis is slightly different than the definition of ergodicity. The definition of ergodicity is just the equivalence of time average and ensemble average properties. The ergodic hypothesis states that a system will become ergodic in the limit of very long time. In other words, if you have a system that has some sort of transient relaxation that takes place, if you take the limit of infinite time, any of those relaxation processes would be finished, and then the system would become ergodic in that limit of a long time scale. So that is the ergodic hypothesis. Now, how do we apply this to glass forming systems? In order to discuss ergodicity in terms of glass formation, we're going to introduce the concept of the Deborah number, which was first introduced by a physicist named Reiner in a Physics Today article. And the Deborah number is denoted as a capital D, and it is defined as the ratio of the internal relaxation time of the system compared to an external observation time scale. Why is it called the Deborah number? Reiner named it after the prophetess Deborah, who is an Old Testament prophetess, who stated back in this book of Judges, chapter 5, verse 5, that the mountains flowed before the Lord. What does this mean in terms of physics? What this means is that if you, as a human being, go hiking on a mountain or skiing on a mountain, you're doing so with the understanding or the assumption that the mountains are not going to be flowing underneath your feet, that the mountains are static on the time scale of your hike or of your skiing trip. However, it is now known as a scientific fact that the mountains do, in fact, flow, that they flow over the timescales of many millions of years, over geological timescales. Mountains are formed, continents drift, mountains erode. They are changing, but over a much longer timescale that is much longer than a human lifespan. And therefore, if you're to observe mountains on a much longer time scale that is not accessible to us as a human, but would be accessible to, say, the Lord, who can observe this on a time scale of, billions of years, then the flow of the mountains would be obvious. And so that is, telling us that there is some intrinsic time scale to the process, say the time scale on which mountains flow. And then that relative to the observation timescale, which for us as humans is much shorter compared to the timescale of observation that is accessible to the Lord. And therefore, the Deborah number would be different depending upon this relevant timescale. So we have different regimes then of the Deborah number based on this ratio of the internal to external timescale. If we have a liquid has a Deborah number less than 1 because everything that is happening in the liquid is happening on a very fast timescale, so a very short timescale relative to our observation timescale, which means that the numerator here is less than the denominator, which means that the Deborah number is less than 1. This corresponds to an ergodic system because any relaxation process that needs to take place in that liquid is happening on a much faster time scale compared to our observation. And therefore, time averages of properties would be equal to ensemble averages of properties in the liquid because it's able to equilibrate on such a fast time scale. So ergodicity is implying that the system has equilibrated on the time scale of our observation, and the liquid is an ergodic state. Now, as we cool the liquid, the kinetics are becoming slower and slower. This intrinsic relaxation time scale is increasing by orders of magnitude. Eventually, it becomes of the same order as our observation time scale. And when that happens, when the T internal is about equal to the T observation, then the Deborah number is about 1. And when the Deborah number is about 1, there is a continuous breakdown of ergodicity. Because what's happening is that the kinetics are becoming of the same order as our observation timescale. And this corresponds to the glass transition range. This corresponds to the freezing in of the liquid state into the glassy state. And this is really the most fundamental definition of the glass transition, is where we have a breakdown of ergodicity, where we have a conversion from an ergodic system to a non-ergodic system. Then if you continue to cool, the supercooled liquid as it's cooled through the glass transition. Then we have a Deborah number that's greater than 1 because the relaxation time scales are much longer than our observation time. And when that happens, we have a non-ergodic system because time averages of properties are going to be different from ensemble averages in the glassy state. So the non-ergodicity of glass is one of the most fundamental features of the glassy state. And it forms the basis for all of the statistical mechanical descriptions of glass. So non-ergodicity is really one of the defining features of the glassy state. This also defines these two inverse processes, glass transition process, whereby a liquid is kinetically frozen into the glassy state, and then the opposite process is called relaxation, and that involves the relaxation of the glass of this non-equilibrium glassy state to the liquid state. And these are opposite processes in that the glass transition involves imposing some kinetic constraint on the system. Imposing that kinetic constraint causes a breakdown of ergodicity and going from the ergodic liquid to the non-ergodic glassy state. When that happens, there is a loss of the configurational degrees of freedom. So the liquid was allowed to explore many different configurations. Those configurational degrees of freedom are lost when you impose a kinetic constraint on the system, freezing it into just either one configuration or a small number of configurations. And therefore, all the configurational contributions to properties end up being lost. So there is a decrease of the heat capacity in going from the liquid to the glass because of that loss of configurational degrees of freedom. There's a decrease in the thermal expansion coefficient, a decrease of the entropy, because we are no longer able to freely explore all these different configurations. And this is what involves then or causes a falling out of equilibrium of the system. So this is the glass transition. It is a conversion from an ergodic liquid to a non-ergodic glass. It is caused because we are imposing some kinetic constraint on the system by observing it on a finite time scale. It is fundamentally a kinetic transition, but it has thermodynamic consequences because of the loss of configurational degrees of freedom, and this necessarily involves a falling out of equilibrium. The relaxation process is the opposite process. This is a spontaneous process that involves going from the glassy state to the supercooled liquid state. This is a spontaneous lifting of the kinetic constraint or a restoration of ergodicity, which is consistent with the ergodic hypothesis, stating that the system will become ergodic in the limit of long time scale. This relaxation process involves exploring different configurations because if we wait on longer and longer timescales, that gives the system more time to explore new configurations. And over a longer enough timescale, this involves a thermodynamic equilibration of the system. And for both of these processes here, there are two factors that we need to consider that involve the kinetics of the system and the thermodynamics of the system. This shows you an example of the thermodynamic consequences of the loss of ergodicity. This is the heat capacity curve of glycerol, which is a simple organic glass former. What you see is the heat capacity as a function of temperature. This shows the liquid at high temperatures, and then as this liquid is cooled below this temperature, which is like 180 something Kelvin. This is the glass transition range for glycerol. You see that there is a loss of ergodicity, which involves a freezing in of the configurations of the liquid into the glassy state. And when those configurations become frozen, there's a loss of the configurational contributions to the thermodynamic properties, and therefore a rather sharp drop in heat capacity, because at low temperatures here, the only contribution to the heat capacity is due to vibrations, since different configurations are not accessible. So this loss of heat capacity here, this corresponds to the loss of the configurational part of the heat capacity. And this is the regime where ergodicity is broken as the system undergoes the glass transition. How do we describe the statistical mechanics of non-ergodic systems? Um, the first, uh, the first theory to describe this was published by Richard Palmer, who was a physicist at Duke University, and he published this in a paper called Broken Ergodicity back in 1982. This is a great paper. I definitely recommend checking it out. And he introduced this notion of broken ergodicity, where he proposed that a non-ergodic system could be broken up into different components where each component would satisfy a condition of internal ergodicity. Hence this notion of broken ergodicity. So what Palmer proposed was that the entire phase space here could be described as the union of disjoint components, where this alpha here is meant to describe different components. And then these components represent regions where internal ergodicity is satisfied. For example, suppose that you have say an energy landscape that looks like this, where you've got different configurations along the x-axis and then different energies along the y-axis. And you've got a group of microstates here on the left with really small activation barriers between those microstates. That is defined to be one of the components here, component alpha, because within that component alpha, the barriers are very small, which means that the time scale for exploring different configurations within the component is fast. Then there is a second component here, component beta on the right, because within this component, the configurations are also easily accessible within the component. However, there's a very large barrier between the two components, which means that the time scale for transitions between components is extremely small. Now, Palmer's notion of broken ergodicity has two main assumptions. The first is internal ergodicity. And internal ergodicity means that if we define an observation timescale, t observed, that observation timescale is much longer compared to the timescale for transitions between microstates within the component. In other words, we're giving the system plenty of time to have a local equilibration within the component such that within the component, ergodicity is satisfied. That is the condition of internal ergodicity. The second assumption that Palmer makes is called confinement. Confinement implies that the observation timescale is much less than the timescale required for intercomponent transitions. In other words, the timescale that's required to transition between components is so much longer than our observation timescale that it effectively doesn't happen. And so that is the second condition of confinement. So basically, Palmer's assuming a hierarchy of timescales, really fast timescales for transitions within a component, an intermediate timescale, which is our observation timescale, and then a much longer timescale for intercomponent transitions. And because of this assumption of internal ergodicity and the assumption of confinement, then any thermodynamic property, such as entropy, can be described as just a weighted summation over the properties that correspond to the individual components. So, for example, if you have an entropy of the system, if it happens to be confined in component alpha, it would have an entropy S alpha based on the number of microstates within component alpha. And then there's a probability of the system being confined in component alpha that is P alpha. Likewise, there would be an entropy of the system if it is confined in component beta. That would be based on the number of microstates in component beta, and that's given by S beta. And then a corresponding probability of being in component beta, which is P beta. And therefore, if you do this weighted average here, where you take the property values within each component, S alpha and S beta, multiply them by their corresponding probabilities, P alpha and P beta, and add them up, that would then give you the expectation value of the property, so the expectation value of the entropy in this case. Now, Palmer's approach was really foundational for the study of non-ergodic systems. However, there are some limitations to Palmer's approach. In many real systems, it is difficult to partition the energy landscape since there's not necessarily a clear separation between slow and fast relaxation timescales. Another issue is that the condition of confinement never strictly holds for any positive temperature because there's always some probability of making any transition as long as the temperature is above absolute zero and the time scale of observation is longer than zero. Also, if you have a system that has a Deborah number near unity, so a Deborah number around one, the kinetics would be too fast to assume confinement, but too slow to assume ergodicity. And so Palmer's approach isn't particularly useful for describing systems, say, within the glass transition range itself, where that Deborah number is close to one. And so real systems aren't necessarily characterized by having this discrete transition from ergodic to broken ergodic states, but they have instead a continuous breakdown of ergodicity as the system transitions from ergodic to non-ergodic. This is a continuous breakdown of ergodicity. So we published back in 2007 a generalized form of Palmer's approach of broken ergodicity that addresses all of these issues. It's called Continuously Broken Ergodicity. This was published in Journal of Chemical Physics in 2007. And this is based on two types of probabilities that are defined. If you have any arbitrary energy landscape as shown here, it doesn't matter if you can define components or not. Continuously broken ergodicity is not based on defining components. It doesn't use any assumptions of internal ergodicity or confinement. Rather, we have one set of probabilities, which are the PIs. The PI would be the probability of the system occupying a given microstate I. So that is this basin occupation probability, PI. And then if you allowed the system to evolve for some observation time scale, over some observation time t observed, if you were to start in a particular microstate I, the second probability is the conditional probability Fij, which is the conditional probability if you start in basin I that you would end up in some basin J after propagating the system for that amount of time. And this is a valid framework regardless of the topography of the landscape, regardless of the Deborah number or the time scale in the system. If you have a system that is ergodic, this would recover that ergodicity. If you have a system that is fully non-ergodic, it would account for that as well. And then everything in between. So, for example, if you have the limit of zero observation time, if you allow the system zero time to evolve, that means that whatever basin you start in, that's where you end up in, right? Because zero time has elapsed, and that means the conditional probabilities, Fii, would be equal to 1, because if you start off in I, then you end up in I because zero time has elapsed. Likewise, if you have zero temperature, then no kinetics are going to occur. On the other hand, at the bottom here, if you have the limit of very long observation timescale, this is consistent with the ergodic hypothesis because in the limit of infinite time, it doesn't matter where you start. Equilibrium has no memory. And so for the system after it's equilibrated, the conditional probabilities become the equilibrium probabilities of that final basin. They no longer depend on where you start. So this would be a fully ergodic system that has been equilibrated, and this is captured in the limit of long time scales in this framework of continuously broken ergodicity. And of course, the reason that we have this theory is that it captures everything in between. So if the system is neither fully ergodic nor fully confined, any degree of non-ergodicity can be captured through this theory of continuously broken ergodicity. So let's look at some of these limiting values. If you have a fully confined system, say the limit of observation timescale going to 0, the conditional probabilities become a Kronecker delta function, delta ij, which is equal to 1 if I equals j, or equal to 0 if I is not equal to j. So for a fully confined system, transitions are not allowed. And the ergodic limit, according to the ergodic hypothesis, so this is the limit of an infinite observation time, then the Fij's become the equilibrium PJs, where this no longer depends on I at all. This is just the equilibrium probability of occupying microstate J, and that is given by 1 over the partition function. Partition function is just the normalization factor for the probabilities, and then this Boltzmann probability factor, e to the minus uj, which is the energy associated with microstate J, divided by kT. Now, if we want to calculate the entropy of the system following or in this framework of continuously broken ergodicity, what we can do is define a conditional entropy SI. The SI is the conditional entropy if the system starts in microstate I. So if you start in microstate I, evolve the system for the observation timescale, the conditional entropy, having started in microstate I, depends on all the different microstates it's able to visit from that starting point. And that would be given by the set of Fij's. The Fij's are the conditional probabilities of all the microstates where it can end up after starting in microstate I. And then this Gibbs formula then, using these conditional probabilities, gives us the conditional entropy. Now, if we weight all of those conditional entropies by the probabilities of starting in those microstates I, so the summation here of all the SIs times the PIs, that then gives us the expectation value of the entropy. So this is a generalization of the formula that Palmer developed in his paper on broken ergodicity. So that forms the framework of statistical mechanics of non-ergodic systems. The next thing we want to do is how to describe the statistical mechanics of the non-crystalline structure of glass. Now, one of the, or probably the single most impactful paper on the structure of glass was published by W.H. Zachariasen back in 1932. This paper in the Journal of the American Chemical Society called The Atomic Arrangement in Glass, where he starts the paper by stating, "It must be frankly admitted that we know practically nothing about the atomic arrangement in glasses. Glasses are described as supercooled liquids or as solids. The former term is justifiable from the point of view of physical chemistry, the latter from the theory of elasticity. It seems rather futile, however, to try to decide which of the two descriptions is the proper one to use when we are ignorant about the characteristic properties of the atomic arrangement." Now, because we know now that the structure of glass has a large degree of disorder because of its non-crystalline nature, this means that the structure of glass is not following a perfect unit cell or any unit cell at all. And really, we've got different configurations that are possible according to different probabilities. And so this question of how to model the non-crystalline structure of glass and the bonding in glass is really a very suitable question for statistical mechanics because we don't know the structure exactly. We only know it with different probabilities. Now, what are the underlying probability distributions to describe the structure and bonding in glasses? What I'm going to show you is that the underlying probability distribution is what's called a multivariate hypergeometric distribution. And I'd like to describe this as an analogy. Suppose that you have, say, a bowl of different colored marbles. Let's say that you've got a bowl of 3 different colored marbles. Let's suppose that there are 6 red marbles, 8 white marbles, and 10 blue marbles. And then what we want to do is randomly draw out one of these marbles without replacement. So you take a marble out, you write down what it is that you drew, and then you don't put that marble back. And so since you're not putting it back, that actually changes the probabilities of the marbles remaining in there since one of the marbles has been removed. So this is let's suppose that we do this n number of random draws. So you draw this out n times, and then you have this finite population, and you're not replacing the marbles. So, for example, what is the probability of drawing three red, four white, and two blue marbles from an urn that contains six red, eight white, and 10 blue marbles? So you've got this bowl or this urn. It's got six red marbles, eight white marbles, and 10 blue marbles. What is the probability then of drawing, if you take, say, nine total draws, that you've drawn exactly three red, four white, and two blue marbles? That's described by a type of statistics called hypergeometric statistics. This is the statistics that is without replacement. And this probability here of drawing three red, four white, and two blue is given by this product of these three binomial terms here. So this is having six red marbles, and then you draw three of them, eight white marbles, drawing four of them, and then 10 blue marbles, drawing two of them. And each of these are the binomial operators. And then you've got the product of doing all three of these at the same time, divided by the total number of possibilities of taking nine draws out of 24 total marbles. And that ratio then gives you that probability, which in this case is 0.048. So it's a 4.8% chance of drawing three red, four white, and two blue marbles on taking nine draws. Um, Now, this is, I'm proposing this as an analogy to glass structure, because what if each of these different colored marbles is a different element in the glass? Like, what if, for example, one of the colors is silicon, one of the colors is aluminum, and one of the colors is boron? And now you start to add network modifiers to the glass structure, like you then drop one sodium ion into that glass. That sodium ion sees that it has three different types of network formers that it can associate with, and it can do different things in the glass structure depending upon which network former that it associates with. So it could create a non-bridging oxygen on a silicon. It could charge stabilize aluminum as a tetrahedral configuration. It could convert boron from threefold to fourfold coordination. And the final structure of the glass, the final properties of the glass depend on the distribution of, if you have, say, n of these sodium ions in there, how many of the sodium ions associate with silicon versus aluminum versus boron, because they do different things structurally in the glass network, and that has different influences on the properties. Now, this is complicated by the fact that there's different energetics associated with those different possibilities. So, for example, even if you've got less alumina in the structure, alumina is more energetically favored to grab the sodium ions first because it is so unstable if it's in a non-tetrahedral configuration. So alumina will want to grab all the sodiums first to stabilize itself in a tetrahedral configuration. And so, for example, if the red marbles here represent aluminum, each aluminum ion here may actually be larger compared to the silicon or the boron atoms, where the larger size represents that it's more energetically favorable to draw one. So if you just sort of blindfold yourself, and if one draw of the marble from the urn corresponds to one sodium ion choosing which network former to associate with, even if there's fewer alumina, the fact that the alumina marbles are larger means that they're individually more likely to be drawn. And so we've got two different effects that are happening here. There is the size of the marbles. The size of the marbles represents the different energetics, where larger marbles are more energetically favorable compared to the smaller ones. But then there's the number of marbles, and the number of marbles is the entropic part. So if you've got a greater number of, say, white marbles or blue marbles, then those are more entropically favored compared to the red ones. So in this case here, the red marbles are more energetically preferred because they're larger. Each individual one is more likely to be drawn, but there's a fewer number of them, so they're entropically less favored. So this brings us to what's called a non-central hypergeometric distribution. On the previous slide, where all the marbles were the same size, that means that each individual marble is equally likely to be drawn. And then the only thing that governs the statistics of the drawing is how many that you have of each color, how many marbles of each color. But if the marbles are of different sizes, then each individual marble has a different probability associated with it. And then it's no longer a central hypergeometric distribution, but a non-central hypergeometric distribution. Now, there's two different types of non-central hypergeometric distributions. They're called the Fisher and Wallenius non-central hypergeometric distributions. And the difference is that with Fisher, it's kind of like if you take your hand and you grab a whole bunch of marbles all at once and pull out a bunch of them all at once and then count, okay, how many of the big red ones did I get versus the small blue ones versus the medium-sized whites. This is if each one is uh, taken all at once. However, if you do it kind of one at a time, that follows the Wallenius distribution, where let's say if you've got n draws, rather than doing all n draws at once, you do a first draw, a second draw, a third draw, and so on. And after each draw, the probabilities change because the population of the marbles is different. So it's two slightly different probability distributions depending upon if you take everything at once, where all the probabilities didn't change because you're drawing everything at once, versus doing one at a time, where the probabilities change after each step. Our case for glass structure follows the Wallenius distribution, and that's shown here. This is the probability of drawing a different species I on the omega number of draw here, where you've got different weighting probabilities that are given by the W sub i's, the different number of species here, and then the different number of draws. And so, for example, with this glass structure analogy, suppose that you've got a boroaluminosilicate glass, and you've got a certain number of aluminum atoms, certain number of boron atoms, and a certain number of silicon atoms. The number of atoms is governed by the composition of the glass, so the chemistry of the glass. And the number of each atom dictates the relative entropy. So entropically speaking, which ones are more favorable? From an entropy point of view, which ones are more favorable are just the ones that you have more of because they have a greater possibility of being drawn. But if you then have, say, more favorable energetics associated with alumina, each individual aluminum atom is like it's a larger marble because each individual one is more likely to be drawn, and that is the energetic effect. So we have this competition between energetics and entropic factors, and when we put it all together, the statistical distribution is called a non-central, multivariate, hypergeometric distribution, and it has Boltzmann weighting factors. It's non-central because the individual atoms have different weighting factors because of their different energetics. That's why it's non-central. It's multivariate because there's more than two choices here. We've got three different types of marbles that are the three different types of network formers in the glass. That's what makes it multivariable. It's hypergeometric because this is done without replacement, meaning that once a sodium ion associates with an aluminum, that aluminum is no longer available to associate with another sodium because that bond has already formed. That's why it is a hypergeometric distribution. The Boltzmann weighting factors come in because the Boltzmann distribution is the relevant probabilistic distribution for describing the statistical mechanics of the system. So the Boltzmann weighting factor here, W sub I, is just a Boltzmann probability factor here, e to the minus hi, which is the enthalpy of that particular association, or it could be the potential energy of that particular association, divided by the amount of thermal energy where the supercooled liquid gets frozen into the glassy state. If we take that as the fictive temperature, So if the fictive temperature is the temperature where the supercooled liquid is effectively frozen into the glassy state, then KTF is Boltzmann's constant times TF. That's the thermal energy where that glass transition happens. So this is our energetic weighting factors here, or enthalpic weighting factors. The probability then becomes, so this pi comma omega, the pi meaning the probability of selecting a given, say, network former I. So this could be the probability of selecting a silicon or the probability of selecting a boron or an aluminum for the next sodium ion that comes in. It's going to be 1 over the partition function. The partition function is just shown at the bottom here. That's just a normalization factor for the probabilities. And then times the entropic contribution. This entropic contribution is just the number of atoms that are still available. So this would be the total degeneracy of those atoms, G sub I. So the total number of, say, aluminum atoms minus the number of aluminum atoms that have already been selected. So it's just the total number of atoms that are remaining to be selected that don't already have bonds to the network modifiers. That is the entropic contribution, this entropic prefactor, and then multiplied by this Boltzmann weighting factor that gives the energetic or enthalpic contribution. And when you combine these together, you have the entropic contribution and the enthalpic contribution. And so you've got different relative weights. What largely governs the different weights between entropy and enthalpy is the fictive temperature. So if you've got fast cooling or a high fictive temperature favors entropy. A low fictive temperature favors energy or enthalpy. And the resulting glass structure that you get can be more entropically favored if it is a higher fictive temperature, or it can be more energetically favored if it is a low fictive temperature. And so this is really the basis of the statistical mechanics that governs that balance between entropy and enthalpy as dictated by the thermal history of the glass represented through its fictive temperature. This shows you some example calculations here. The y-axis shows the fraction of network modifiers associated with a given network former A as a function of delta H over KTF. So this would be the enthalpy difference between two different bond associations divided by KTF, the amount of thermal history at the fictive temperature where the supercooled liquid gets frozen into the glassy state. And if you have the limit of this delta H over KTF going to 0, so in that limit, that would mean that there's no effective energy difference between these two different states, or that the fictive temperature is infinite. So in other words, at this limit, we're completely governed by entropy. So the probability of associating with network former A is just a function of the composition of how much A is there relative to the total amount. So the concentration of A over the total concentration of the network former is A plus B. And likewise for the probability of B. So this would be the entropic limit here. If you take the opposite side, so going to a limit of large delta H over KTF, this would be the energetic limit. So you'd have kind of the most chemical ordering in the glass would occur in this limit, because here, this is where you have a large energy difference or large enthalpy difference between modifiers associating with network former A or B, and then everything in between. So it's entirely governed by entropy on the left-hand side, entirely governed by enthalpy on the right-hand side, and then trade-offs between the two in the middle. These statistical mechanics provide a natural description of the mixed network former effect in glasses. The mixed network former effect is a nonlinear variation of glass properties where you have a fixed amount of network modifier here, a fixed amount of M, and you're just varying the ratio of how much of one of the network formers you have relative to the other one. So this x-axis is now the mole fraction of network former A, so it's the concentration of network former A over the total amount of network formers here, A plus B. And then the y-axis shows the fraction of modifiers associated with network former A. And the different lines here are different delta H over KTFs. So zero here, this black line is if you're completely dominated by entropy. The gray line, where you've got a large delta H over KTF, would be the limit of having an energetically controlled structure. And then everything in between here shows where you have some trade-off between entropic effects and energetic effects. And you can see the nonlinearities that occur for anything that has a trade-off between entropic and enthalpic effects. And so that nonlinearity is the mixed network former effect, and that's naturally captured by this statistical mechanical treatment of the glass. It's really easy to extend this to the multivariate case. For example, what if you have three network formers, A, B, and C, and you've got a certain concentration of network modifiers M? What's the fraction of those modifiers that goes for each of those three network formers? And you can see here in this plot that it is a function of both the chemistry of the glass in terms of the molar concentrations of each species, as well as the energetic differences. And you can have different regimes where different network formers are either more preferred or less preferred. And another nice thing about this statistical mechanical approach is that it gives you not just the expectation values, so not just the average values of the structural of the expected structure, but also the distribution. So what this means is it's giving you not just an average value, but also the expected fluctuations in bonding. And you can see these fluctuations evolving where if you've got a system that's completely dominated by entropy, if it's completely dominated by entropy, this distribution here is actually a central hypergeometric distribution, because the energetic differences are either non-existent or they don't matter. If you have a delta H over KTF that is not equal to zero, then that central hypergeometric distribution becomes a non-central hypergeometric distribution. And if you take the limit of a really large delta H over KTF, then that actually minimizes the fluctuations as this non-central hypergeometric distribution kind of collapses into a delta function in that limit. And you can also use statistical mechanics here to calculate the evolution of structure over time as the glass relaxes from its initial fictive temperature, TF0, to some new fictive temperature, TF, in the limit of time going to infinity. Then statistical mechanics can be used to describe how the glass structure is evolving as a function of time following this relaxation from its initial fictive temperature to some new temperature as it equilibrates. Now, the next step of describing the statistical mechanics of glass is what's called topological constraint theory. Once we know the distribution of structural units in the glass, now we want to know how that distribution of structure influences the properties. And that connection can be made through topological constraint theory. This was originally proposed by Jim Phillips back in 1979, and he did it initially in the context of chalcogenide glasses, specifically looking at germanium selenide systems, where what he did was to count up the number of rigid bond constraints in the glass, where if you've got, say, a tetrahedron around germanium, you count the number of rigid bonds here around the germanium. You also count the number of rigid angles that can occur around the germanium or around the selenium. And if you add up the total number of these rigid constraints, so add up all the rigid radial constraints and all the rigid angular constraints, Phillips proposed that the optimal glass formation should occur where that total number of rigid constraints is equal to the total number of the atomic degrees of freedom. So every one of these atoms here has 3 degrees of freedom if it exists in 3-dimensional space, because each atom can move in the x direction, the y direction, or the z direction. Every time you subject this to a rigid bond, it takes away one of those degrees of freedom. And if you have a number of rigid constraints exactly equal to the number of degrees of freedom, then you've got a perfect balance. And this is what's called an isostatic system. And Phillips postulated that this would be the best glass forming system. And a lot of work had been done to validate or to test Phillips's theory. Now, Phillips's theory was a zero temperature theory, and if we want to apply this um, to systems at finite temperature and to predict how properties are evolving with composition and with temperature, we need to generalize this. And the generalization of this theory was developed by Prabhat Gupta and myself, and it's called temperature-dependent constraint theory. And the base equation here for temperature-dependent constraint theory is that the number of constraints per atom, this little n, is a function of the temperature of the system T and the composition of the system X. And this number of constraints per atom is going to be equal to a double summation, where the outer summation is over all the different species of the glass, all these species I, and their corresponding mole fractions. So n sub I would be the molar fraction of each of the species. That is only a function of the composition X. And then for each one of those species, we have a summation over all the different types of constraints alpha. So these would be all the radial constraints and all the angular constraints. And each one of those types of constraints alpha would have a number of constraints associated with it. So say the number of radial constraints or the number of angular constraints. That's Wi alpha. So for species I in constraint type alpha, that W gives you the number of constraints. And then a temperature-dependent constraint function Q sub alpha, which is a function of T. So the parameters that we need to use this theory are the mole fraction of each network forming species. We get that from our statistical mechanics that section that we just finished. This follows a non-central hypergeometric distribution as we described. The total number of the alpha type constraints for each species I, and then the temperature dependent constraint function. That temperature dependent constraint function looks like this. So this shows the rigidity of a constraint going from 1, which is a fully rigid constraint, down to 0, which would be a floppy constraint that's providing 0 rigidity of the system. Any constraint function has the limiting behavior that in the limit of absolute 0 temperature, any constraint would be rigid, because even weak bonds must be rigid if you have the limit of an absolute 0 temperature. So the limit of T goes to 0. This constraint onset function would be equal to 1. In the opposite limit, in the limit of going to infinite temperature, there the system has an infinite amount of thermal energy to overcome any constraint. And so in this limit, the constraint onset function here becomes 0. So it's the limit of 1 and the limit of low temperature, and the function goes to 0 and the limit of high temperature. That means that there needs to be some transition in between the two. This can be described in continuous form as shown here, where the constraint onset function Q of T is basically described by this Boltzmann distribution here, 1 minus the Boltzmann distribution. So this is the probability now of being confined instead of the probability of escaping. And this is the probability of remaining confined over some observation time T observed. This tends to be a relatively sharp function, which means that we could approximate this continuous function as a unit step function. This theta is a unit step function here, where it is 1 at all temperatures below this onset temperature TQ, and then it's equal to 0 at all temperatures that are above the constraint onset temperature TQ. Turns out that both of these descriptions are useful. So it's useful to consider the discrete form for cases like describing how the glass transition evolves with composition. The continuous form is actually useful for some other temperature-dependent properties. And so they both have their place. And it's straightforward to convert between the discrete and continuous forms if you consider that they both have to pass through 1/2. They both have to pass through a 0.5 here at the constraint onset temperature. So if you take a constraint onset temperature T alpha, you can solve for this free energy barrier here, delta F alpha star. It's just equal to minus T alpha times the natural log of 1 minus 2 to the power 1 over the vibrational frequency here, nu times the observation time. Let's take a simple example to see how this works. Consider the alkali borate system. And borate systems are interesting because of this so-called boron anomaly. Boron can exist in threefold coordination or in fourfold coordination. And when you add an alkali modifier to a borate glass, it can take on two different structural roles. It could convert the boron from a threefold coordination to a fourfold coordination, as shown here. When that happens, the connectivity of the network increases. It increases the glass transition temperature, and so on. The other option is that adding modifiers to the borate glass can actually break up bonds. It can form non-bridging oxygens, where now instead of having three bridging oxygens here on the left, it creates one non-bridging oxygen so that there's only two bonds here to other units. This actually decreases the connectivity of the network. And so what makes the boron anomaly so interesting is that modifiers could either increase the connectivity of the network or decrease the connectivity of the network, depending upon their specific structural role. Now, Prabhat Gupta developed a model that describes what is the fraction of boron in different coordination states. It's called the random pair model, and it's based on the notion that the tetrahedral boron units, the BO4 units, that these occur in pairs, and that the pairs of BO4 tetrahedra cannot be bound to each other, and that non-bridging oxygens occur only in the trigonal groups, the BO3 groups, and not in the tetrahedral BO4 groups. And mathematically, the random pair model gives us equations that describes how many of the borons are in Q3 units, meaning these are trigonal borons with three bridging oxygens, versus Q4 units, which are the tetrahedral boron groups, versus Q2 units, which are the trigonal boron units that have one non-bridging oxygen and therefore only two bridging oxygen reflected in the superscript here too. And what we see with the random pair model is that all the borons start off in Q3 units here if you have zero modifiers. As you increase the modifier content here, X, initially borons convert from trigonal to tetrahedral coordination. This increases the connectivity of the network, and this continues until you get to this 1/3 concentration of modifiers where the population of Q4 units is equal to the population of Q3 units. At this point in time, it's not possible to form additional Q4 units and still satisfy this rule that pairs of BO4 tetrahedra cannot be bound to each other. And what this means is that beyond this point, at X greater than 1/3, we are forced to form Q2 units. We're forced to form non-bridging oxygens. And because of having fewer bonds available, because of the non-bridging oxygens, the population of tetrahedral units also decreases. So we can use this then to give us these equations here that show the evolution of the three different types of boron units here, Q2, Q3, Q4, and also account for the number of bridging oxygens here. This OB is the population of bridging oxygens. And so if you include the bridging oxygens here, and then the three different types of borons, this plot gives us the fraction of each type of network-forming species following the random pair model. And these equations then can be used as input into the temperature-dependent constraint model. The next step is to define the hierarchy of constraints in the system, starting with, starting at high temperatures. This plot shows the atomic degrees of freedom versus composition, where the X here is the mole fraction of the modifier oxide, and then the different lines are showing different temperature regimes. And where we start is on the red line. The red line is at high temperatures that are above the constraint onset temperature for the strongest constraint. The strongest constraint in the system is the linear bond between the boron and the oxygen. And there are two of these alpha constraints, two of these linear constraints at each bridging oxygen. And so if we start at temperatures that are hotter than that, all the constraints are broken. That means that regardless of the composition, there are three atomic degrees of freedom per atom because there are no rigid constraints. So all three degrees of freedom, the X, Y, and Z degrees of freedom, are all available to the system. But if you cool the system where the temperature falls below T alpha, that means that these linear bonds are now providing rigidity in the network. And that means we go from the red line here down to the green line. The green line shows temperatures that are less than T alpha. That means that the alpha constraint, the strongest constraint, is rigid, but we're still at temperatures above T beta, so above the second strongest constraint. The second strongest constraint, T beta, the next one is the angular constraint around the cation. So this is the OBO angular constraint. There's five of these at each Q4 unit in a tetrahedron. There's three of these at each Q3 unit in the trigonal configuration, and then only one of them in a Q2 unit. And so when the system is then cooled below T beta, we go from the green line down to the blue line. And then if you continue to cool, the next strongest constraint is the angular constraint around the oxygen, the BOB constraint, and there's one of these at each bridging oxygen, and that would take us from the blue curve to the purple curve. So this graph is really interesting because it shows us the composition dependence in terms of X, and it shows us the temperature dependence as we cool the system from high temperatures down to lower temperatures. As that cooling takes place, we are losing atomic degrees of freedom as we get more and more rigid constraints in the system upon cooling. Now, the glass transition temperature has to occur where we've got some rigid constraints in the system, but it's not yet fully rigid. And so mathematically, we can determine that the glass transition temperature must fall between the T gamma and the T beta. So at the glass transition temperature, two types of constraints are rigid, the BO constraints, which are the strongest, and then the angular constraints around the boron, so these T beta constraints. However, these weak constraints, these weak angular constraints around the oxygen, are still too weak at this point. So TG is falling somewhere in between the two. And this mathematically is determined based on these two conditions that the number of degrees of freedom at the glass transition temperature must be less than 3 in order to induce a glass transition, but still must be greater than 0 if the system is still experiencing flow. So we know it must be between 0 and 3. And also we know that that the glass transition temperature, the derivative of that with respect to the modifier concentration must be positive and at x equals 0 because of the formation of tetrahedral units. And therefore, with these two conditions, we've deduced that that's where the TG must be. Now, putting this all together into temperature-dependent constraint theory, we use the formulas from Gupta's random pair model, use all of the rigid constraints, the rigid alpha constraints and the rigid beta constraints, and that gives us then a formula for the number of rigid constraints per atom in the glass transition region, which is shown here. And then 3 minus that gives us the topological degrees of freedom, because if you start off with 3 degrees of freedom, every time you have a rigid constraint, it takes away one of those degrees of freedom. So 3 minus n gives us f, the topological degrees of freedom. According to temperature-dependent constraint theory, the glass transition temperature can be calculated through this evolution of the topological degrees of freedom, where if a system has more degrees of freedom, that actually lowers the glass transition temperature because it's easier for the atoms to move around. If the system has a lower number of degrees of freedom, that means it's more rigid, and that means the glass transition temperature increases. And so using this formula, we can calculate the evolution of the glass transition temperature as a function of the modifier content here, X, relative to some reference TG. And this is this is a piecewise function according to the random pair model, where in this regime it's relative to the TG of the pure B2O3, and at this one it is the TG of the 1/3 composition, which is the diborate composition. We can solve for TG of 1/3 in terms of the original part of the piecewise function, since it has to be continuous, and then express the equation just in terms of a common reference point TG of 0. And if we plot that function, this shows the temperature that would be predicted here. This is TG of 0, which is the measured glass transition temperature of pure B2O3. That is equal to 543 Kelvin. And if you plot that function, you follow this black curve up, and it actually keeps going along the blue curve, peaks at the diborate composition of x equals 1/3, and then comes back down, where what's happening here is that the initial addition of alkali is converting boron from threefold to fourfold coordination. That increases the conductivity of the network, which increases the glass transition temperature until it peaks where you've got the peak concentration of tetrahedral boron, and then as you start to form non-bridging oxygens, the glass transition temperature comes back down again. There's one complicating factor, though, is that eventually the glass transition temperature violates one of our assumptions, which was that it falls below T beta. And in fact, if we have T beta placed somewhere here, if the T beta, if the TG goes above T beta, that means that all of those beta constraints are no longer providing rigidity. If we've heated the system above the temperature where the beta constraints are rigid, then it becomes floppy. And if it becomes floppy, that wants to drive the glass transition temperature back down. But if the glass transition temperature goes below T beta, then those beta constraints become rigid again, and that wants to drive it back up. And the result is that if this TG curve tries to cross T beta, it basically gets stuck there at exactly equal to T beta, because every time it goes above T beta, those constraints become floppy and it wants to drive the TG back down. But when it goes back down, those constraints become rigid and wants to drive the TG back up. And so instead of following this blue curve, basically we follow the black curve where the TG rises until it hits T beta. Then it gets stuck at T beta until there are enough non-bridging oxygens for the glass transition temperature to go back down again. That gives us this final equation for the glass transition temperature as a function of x, where basically we need to know what TG of 0 is. This is the measured glass transition temperature of B2O3, and then we need to know what T beta is. And that can be deduced quite easily by just looking at the experimental data, where you can see that, in fact, there is a flat region here of the glass transition temperature as a function of composition. So this shows experimental data are the points versus the model, which is the black curve, and that is an analytically derived model using temperature-dependent constraint theory. So this shows you the power of both temperature-dependent constraint theory and, in general, statistical mechanics to be able to predict the evolution of property values. And it's not just glass transition temperature, too. For binary systems, it can easily be extended to ternary systems. This shows how the TG evolves for soda-lime borate. So this is a sodium-calcium borate system. It can be extended to get other properties like Angel's fragility index. This shows the evolution of fragility index in soda-lime borate systems. It can predict mechanical properties here. This shows the evolution of glass hardness, where the glass hardness is proportional to the number of rigid constraints at the temperature where the hardness is measured, which is usually room temperature. This plot on the left shows a linear relationship between measured hardness and the number of atomic constraints per atom. And if you change that x-axis to be a compositional axis instead of a number of constraints, you can see that this captures the boron anomaly with respect to hardness, where you've got an initial increase in hardness. As you get more tetrahedra, that increases the connectivity of the network as there's more rigidity until it peaks at where the number of tetrahedra peak, and then the hardness goes back down where non-bridging oxygens start to form. This approach through temperature-dependent constraints provides a natural explanation for why properties vary differently, like why hardness scales differently than glass transition temperature. It's even though they both depend on the connectivity of the network, hardness depends on the connectivity of the network at room temperature, and glass transition temperature depends on the number of constraints in the network at elevated temperatures in the glass transition region. And that's why these properties scale differently, even though they both go back to the number of constraints. So that does it for this lecture. My goal was just to give you a flavor for some of the things that are involved with the statistical mechanics of glass. To summarize, statistical mechanics offers explanation and prediction of properties of glasses based on its microscopic physics. So based on the different configurations that it can adopt and the probabilities of adopting those. The basic thing that we have to account for is the broken ergodicity of the glassy system. And the generalized theory for that is called continuously broken ergodicity. That is applicable for any system of any composition with any type of energy landscape having any topography. And it is valid in the limit of a fully ergodic system, a fully non-ergodic system. And then if we look at the structure of glass, the non-crystalline structure of glass can be described in terms of probability distributions that follow a non-central hypergeometric statistics. And if we calculate that, it can plug into topological constraint theory and specifically temperature-dependent constraint theory, then to calculate properties. So this kind of gives us the framework to go from the really basic underlying physics of the non-ergodicity of glass up through understanding the distribution of glass structure and bonding, connecting that then to the connectivity of the glass network and the number of rigid constraints or degrees of freedom, and then the properties of glass. And this, we're just scratching the surface here. If you want to learn more, please check out this review article, Statistical Mechanics of Glass. This is an open access article available in Journal of Non-Crystalline Solids. So this is freely available for anyone who would like to check it out. And if you have questions, please let me know in the comments. I will be happy to address them. All right, thanks everyone. I hope you enjoyed the lecture and I hope you found it interesting. I'll see you next time.